using the dual, solve the following linear programming problem. So I am audible. I,
Yes, sir.
Yes, sir. Yes, sir, you're audible.
okay. So first you see, using the dual, solve the using the dual, solve the following LPP. Okay, so here max ZP means maximization problem 3x1 plus minus twice x2 such that x1 less than or equal to 4, x2 less than or equal to 6, x1 plus x2 less than or equal to 5, minus x2 less than or equal to minus 1, and x1 comma x2 greater than or equal to 0. Okay, so first you see our problem is what. So here you see, using the dual, solve the following linear programming problem. So first write its dual. Okay, and first you check whether the given problem is standard primal form or not. So this problem is standard primal form or not. What is the standard primal form? What is the standard primal form? Arif, Roshni, what is the standard primal form?
When it's
Purpose?
greater than or equal to, then the problem should be maximization, and for minimization, it should be greater than or equal to.
Greater than or equal to. Okay. So here you see our problem is maximization, right? And here all constant sign is less than or equal to. All constant sign is less than or equal to. So this is the standard primal form. So here you see, you will not confuse, this is using the dual, solve the following linear programming problem. This is not the method of dual simplex algorithm. This is separate one. This is the separate one. Using the dual, solve the following linear programming problem. And using dual simplex algorithm, solve the following LPP. This is different one. Okay. So here you see our first maximization, all constant sign is less than or equal to, right? So dual, first you write its dual. So here you see I have written directly its dual. So what is its dual? Here maximization problem, so its dual will be minimization, right? So the dual of the given problem is given by mean ZD. Okay, mean ZD. So here you see mean ZD equal to, here coefficient of the objective function and constant are interchange. So this one will be 4W1 plus 6W2 plus 5W3 minus W4. So you see constant part is 4, 6, 5 minus 1 of the constraint. So this will be in dual. This is the coefficient of the objective function. So 4W1 plus 6W2 plus 5W3 minus W4. It's okay.
Yes.
such that okay, such that you see, then here number of in the primal number of variable is 2. So in dual number of equation will be 2. You will remember number of variable in the primal is 2, so number of equation in the dual will be 2, and number of inequation is in the dual is 4, so number of here number of variable in the dual will be 4. So this one will be W1 plus 0 into W2 plus W3 plus 0 into W4 means what? You see, all the coefficient of x1 in the primal. Coefficient of first constant of x1 is 1, second constant is 0, third constant is 1, fourth constant is 0. So this one will be rows and columns interchange. So this one will be the coefficient of W1, W2, W3, W4 coefficient, right? Similarly, first coefficient of the primal means x2 is 0, second is 1, third is 1, fourth is minus 1. So this one is 0 W1 plus 0 W2 plus 0 W3 minus W4. Next, in primal symbols are less than or equal to. So in its dual, the symbol will be greater than or equal to, right? So symbol will be greater than or equal to. So here what happened? And next one will be constant will be here objective function of the primal 3, coefficient is 3, x1 coefficient is 3. So here we write in the dual greater first inequation will be greater than 3 and second inequation will be minus 2, right? So this is our dual. Okay, this is the dual of the given linear programming problem. Next, what we do, this min z will be from min z we shall write max z. So max z d dash equal to minus min zd. So minimize z equal to zd is minus 4w1 minus 6w2 minus 5w3 plus w4, such that W1 plus 0 into W2 plus W3 minus 0 into W4 greater than or equal to 3. And second constant is 0 W1 minus W2 minus W3 plus W4. And here you see in the second constraint in the dual, second constant is minus 2. So by simplex method, always we make it into the positive by multiplying minus sign. So when we multiplying minus 1 by both sides, then inequality will be changed and this one will be 0 will be same 0 into W1 minus W2 minus W3 plus W4 less than or equal to 2. And next what we do, we introduce a surplus variable in greater than symbol equal to present here. So surplus variable and second constant we use the slack variable. And what happen here you see, identity matrix is already we got identity matrix, so no need to introduce artificial variable in the first constraint because w1 and coefficient of w6, coefficient of w1 and coefficient of w6 gives us the identity matrix, right? Gives us the identity matrix. So next, we consider in the second page, you see which variable is equal to 0. Here, total number of variable is 6 and equation is 2. So, 6 minus 2 means 4 variable is equal to 0. Then we consider W1 equal to 3 and W6 equal to 2. Right. So, in the first table, we make in this way B C B. B will be W1 W6, CB will be minus 4 0. And WB is W1, W2, W3, W4, W6 like this. Next, you put all the coefficient of W1, W2, W3, W4 and W6, right? Next, you find out delta J. Okay, and when we find out the delta J, then you see in W4 column, this gives us the positive value. So for this region, we find out the minimum ratio. So minimum ratio, how to find out? WB by incoming vector. So incoming vector is W4, so this is W4. Then WB by W4, first ratio is infinity, will not write. Second ratio is uh, 2 by 1 means 2. So this is our minimum ratio row, means key row. So here intersecting element is W1. Intersecting element is 1, means outgoing vector will be W6 and intersecting element is 1. So up to this clear? Anybody you have any doubt?
No, sir.
Yes, sir. Anuj? So here you see, next one will be, next what we do here, outgoing vector will be W6. So W6 will be out and this is replaced by W4. So W6, then it replaced by W4. So you see in B, second table, in B column W1, W4, and CB we write -4, and coefficient of W4 in the objective function is 1. So write 1. Then how to write the, first we write the second row. Second row means W4 present in this row we fill up. So this is our key row or outgoing vector, and this divided by the pivot element. So our pivot element is 1. So 2 by 1, 0 by 1, minus 1 by 1, minus 1 by 1, 1 by 1, then 0 by 1, 1 by 1, right? So this one will be what? This one, first W4 row complete. Next we fill up the first row. So how to fill up the first row? Then new element equal to old element minus intersection of key row key column. So here you see 3 minus 0 into 2 divided by 1. So always this is multiplied with 0. So first row will remain same. So here you see first one is 3, second one is 1, then 0, 1, 0, minus 1, 0, 0. So this is always multiplied with 0. So this remains same. So next, we find out delta J and Z D dash. Z D dash is -10 and delta J. So since all delta J less than or equal to 0, so this solution of the dual problem is optimal. That is, optimal solution of the dual problem is here W1 equal to 3, W2 here W2 is absent, so 0, W3 is 0, W4 is 2. Okay, and mean ZD, how to write mean ZD? Mean ZD equal to minus makes Z dash, ZD dash. So minus minus plus, so 10. Then how to write its primal solution? So primal solution we shall write its surplus variable in delta J, in surplus variable and slack variable. So W5, what will in W5 is our surplus variable and W6 is the slack variable. So here x1 will be minus delta 5. So this is negative sign. We know how to read the primal from the dual. So x1 equal to minus delta 5. So delta 5 is minus 4. So minus minus plus 4. And x2 is minus delta 6. So this is minus minus plus 1. Therefore, maximum ZP equal to mean ZD equal to, we get the value 10, because max ZP equal to mean ZD. Because how to write the dual, means how to write the primal solution from the dual. I have given the procedure how to read the solution to the dual from final simplex table of the primal and vice versa. Here you will see delta j with sign changed for slack or surplus variable in final simplex table. For the primal are the values of the corresponding optimal dual variable in the final simplex table. And max zp equal to mean zd. So max zp equal to mean zd value is 10. So this is the solution. Now you can solve now using dual how to solve the linear programming problem. Another, you will not confuse, there are two problem. One is using the dual solve the linear programming problem, means first you convert it into the dual, then you solve, and again you convert it, write the solution of its primal. So when we write the solution of its primal, then you will write x1 x2 variable in terms of delta j, means in which delta j, those are slack or surplus variable. And dual simplex method is totally different. Okay, and next one is, what is the advantage of dual simplex algorithm? Anybody, any idea? In simplex method and dual simplex method, any difference have you got?
Faster as compared to simplex method.
Okay, so in dual simplex algorithm and simplex method, you see, when for from the first table move to the second table, then you will see in simplex method we find out the minimum ratio. But in dual simplex algorithm, without finding the minimum ratio, we can assign which one is the key row and incoming vector. Clear? We can, and also we can identify our pivot element in dual simplex algorithm. But in case of simplex method, when all at least one delta j is positive, then we find out the minimum ratio. Without finding the minimum ratio, we cannot get the solution, right? So this is one of the major difference. And you will do practice, means a table you will practice how to, from the old table, how to calculate the new table. Start transportation problem. Okay, response your name, Oboni Boro.